In 1843, a mathematician was walking across a bridge. Suddenly, he imagined a new mathematical language for 3D rotation. Immediately, he carved the equations into stone, introducing three distinct imaginary units. No one knew it then. This strange number, the quaternion, would one day guide SpaceX rockets and power the rotations inside the 3D games. So, why did great minds choose quaternions, not matrices, to describe three-dimensional rotation? Here are 5 mathematical reasons why. Number 1. 3 independent axes. Think back to the complex plane. If you multiply the real number 3 by the imaginary unit I, you get 3i. Geometrically, the point 3, 0 moves to 0, 3. Since I equals cosine 90 degrees plus I sine 90 degrees, that's exactly a 90-degree rotation about the origin. Multiplying z by cosine theta plus I sine theta represents rotating z by the angle theta. In 2 dimensions, there's only one rotation axis, z-axis, so one imaginary unit is enough. But in 3 dimensions, there are 3 independent rotation axes, so quaternions introduce 3 engines instead, I, J, and K. Each of them squares to -1, which tells us that they are all imaginary units, which represent rotation. But the fact that they are different means they correspond to different axes. I for rotation about the x-axis, J for rotation about the y-axis, K for rotation about the z-axis. Actually, they are 180-degree rotations about their respective axes. The moment we represent the point 3, 8, 4 as the quaternion 3i plus 8j plus 4k, that point is now ready to rotate in any direction in 3D space. Number 2. Composition of rotations. Take the point, rotate it 90 degrees about the x-axis. Then 90 degrees about the y-axis. The z component appears, even though none existed before. The axes are independent, but their rotational effects interact. This behavior matches the quaternion multiplication perfectly. When 2 imaginary units are multiplied, a third one is produced. I and j represent 180-degree rotations about x and y respectively. Then, the product ij represents a rotation about y, followed by a rotation about x. Notice that in quaternion algebra, the order of multiplication is the reverse of the order of rotation. The result is k, which corresponds to a 180-degree rotation about the z-axis. With a single quaternion multiplication, compound rotations involving multiple axes are handled automatically without any extra correction. Number 3. Non-commutativity. Rotate 90 degrees about the x-axis. Then 90 degrees about the y-axis. The z component becomes negative. Now reverse the order. Rotate about y first, then about x. This time, the z component is positive. Same angles, different order, completely different result. That's because 3D rotations are extremely sensitive to order. Quaternions encode this rule directly in the algebra. ij equals k, but ji equals -k. The commutative law of multiplication doesn't hold. Reversing the multiplication reverses the direction. This algebraic asymmetry is exactly what allows quaternions to handle real-world rotation sequences correctly. Number 4. Complex rotations reduced to 1. Rotate around x, then Y, and finally Z. But the 3 consecutive rotations are equivalent to rotating the point about this single axis by about 90 degrees. This is Euler's rotation theorem. The Quaternion Q is the most compact expression of this idea. The real part W encodes the half angle of the rotation. The imaginary part XYZ encodes the direction of the rotation axis. 3 consecutive rotations are compressed into one quaternion. While a rotation matrix needs 9 numbers, a quaternion needs only 4. Number 5. Isometry. A rotation must not stretch or distort an object. Lengths and distances must stay exactly the same. Quaternion rotations guarantee this. For a point P, the rotate point P' is defined as P' equals Q times P times Q inverse. Q inverse is the quaternion conjugate of Q. Both Q and Q inverse have magnitude 1. They are unique quaternions, so this operation preserves norms perfectly. Not a millimeter of distance is changed. Quaternions alter only direction, making them the most honest rotation tool possible. There's one more practical reason we use quaternions instead of Euler angles. In Euler-based systems, at certain angles, 2 rotation axes can align and collapse into one. One axis effectively disappears. This is Gimbal lock. But quaternions represent rotation as a single number. No matter the angle, the axes never collapse or interfere. That's why quaternions are essential in 3D games, spacecraft attitude control, and any system that demands smooth, continuous rotation. Now you see why quaternions are perfectly suited for 3D rotation. They are the very language 3D rotation was always asking for. Now you finally speak it. Thank you.